So yeah, the weather is pretty hot, so let's do something cool. Thank you very much for the introduction, and thanks everyone for coming. My name is Khanh, and I'm very excited to be here, especially because I'm Polish. So today I will talk about zero-knowledge proofs, why they are interesting, and how can we build them from lattice-based assumptions. Okay? Okay, so let's use this. Okay, so the overview is the following. We will start with the motivation of zero-knowledge proofs. I will also discuss snarks, because it's a hot topic in cryptography in recent years. We will have a very simple example of zero-knowledge proofs. Then we will build some nice zero-knowledge proofs for lattice-related statements. And one of the applications will be the lithium signature scheme, which is one of the NIST standardized schemes. Okay? So what is a proof? Well, we're all here mathematicians, computer scientists, right? So when we think of a proof, we really think of a mathematical proof. So you have some theorem, which is some statement, and then there's the proof that this theorem holds, right? But there are also other proofs in real life, like piece of evidence, which is used in an investigation, or even if we want to go to a pub or a club, then it's only we need to show our ID to prove that we are over 18. Okay, so a simple definition from a dictionary actually is that the proof is a fact or a piece of evidence that shows that something is true or something exists. Okay, so in computer science, this has been modeled in the following way. So we start with a thing which is called interactive proof. So in the interactive proof, we have two parties, the prover and the verifier, and both parties have the statement X. So let's just think of it as a theorem, mathematical theorem. And then the prover also has the witness W. Okay, so W should be a valid witness such that they X and W satisfy some relation. Okay, so for example, W is a proof, like a mathematical proof. Okay, so as the name suggests, it's an interactive protocol. So two parties communicate with each other, and at the end, the verifier accepts or rejects. Okay, so obviously, like for completeness, if we want to consider honest provers, we want to make sure that an honest prover can, if an honest prover executes this protocol, then the verifier accepts. We will deal with the case of cheating provers later. Okay, so that's the interactive proof. A non-interactive proof, as the name suggests, is when there's only one round of communication. So the prover just outputs the proof pi. Okay, so that's only one round. We're still interested in things like completeness and so on. So the next step is about succinctness. So succinctness says that this proof has to be much shorter than the size of the witness. And why is it interesting? Well, because if we don't care about succinctness, then in principle, the prover could just send the witness in the clear, right? So the prover could just send the witness. Obviously, it satisfies completeness. The verifier would just manually check whether this witness is valid. Okay, so for interesting applications, we want the proof to be much smaller than the size of the witness. And then completeness, okay? And the last part is argument of knowledge. So let's start with proof of knowledge. So we say that a non-interactive proof satisfies proof of knowledge if it satisfies a thing called knowledge soundness. So knowledge soundness says that if a prover can convince the verifier with high probability, that it essentially must know the witness. Okay? So in other words, if a cheating prover doesn't know the witness, but somehow wants to cheat, then at the end of the day, it can't convince the verifier with high probability. Okay? And then we say argument when knowledge soundness holds under a computational assumption. So in the end, all these combined, it gives you a snark. Okay, but then what about zero knowledge? So we have this non-interactive proof about some statement, but what if this statement or like the witness contains some sensitive information, right? For example, if we want to prove that we are over 18, but like in principle, we could just show our ID card, right? But the verifier could see some sensitive information, For example, that someone is like 30 years old, or like lives in London, or like some other, so they can see date of birth, they can see the address, and so on. And this could be some sensitive information. Okay? So with zero knowledge, we want to make sure that we want to convince that the statement is true without revealing any sensitive information about our witness. Okay? So with the zero knowledge proof, the verifier shouldn't learn any information about the witness or any information apart from the statement that something holds, like that we are over 18. Okay? So what are applications of zero knowledge proofs? There are a lot of them, so I just provided some simple ones. So the first one could be some sort of confidential transaction or payment system. Okay, possibly we may want to build a payment system where we don't want to reveal, for example, the amount. We just want to make sure that we can spend less than how much money we have in the bank account. So this is some kind of range proof. Or we want to hide identity of a recipient or the sender. So this is also some form of set membership proof. Okay, another simple example would be electronic voting, where we want to, first of all, we want to prove that we are a valid citizen, valid resident to vote, without revealing information about, let's say, our residential address. But also when we want to prove that our vote was encrypted correctly, that it was indeed either yes or no in a referendum, 0 or 1, and not just 100, okay? So that's the electronic voting case. And similarly for anonymous credentials, when we want to obtain, for example, a student discount or a senior discount, and we want to show that we're eligible for it, but without revealing any information about other data. Okay, and one particular example that European Commission is currently interested in is a digital identity and digital wallet. And so they have this interesting project, and they have asked various experts around the world whether we can build something like this using zero knowledge proofs. Okay. So now we turn to a very simple example, so that let's start very simple. So we have this experiment. So there's a statement like, I know how to distinguish between Pepsi and Coke. Okay, so maybe can you raise your hand if you prefer Coke than Pepsi? Okay, cool. And can you raise your hand if you think you can distinguish Coke from Pepsi? Which should be the same, right? Okay, so decent number of people. So the experiment is usually like this. Like in a classroom, it's more interactive, but yeah, it takes time. So the experiment would be like this. So the verifier prepares a glass of either Pepsi or Coke, so it just flips a coin. If it's 0, it's Pepsi, and if it's 1, it's Coke. And then the verifier gives this glass to the prover, and the prover drinks it and decides whether it was Pepsi or Coke. So it sends the bit B prime, and the verifier is convinced that the prover knows how to distinguish between Pepsi and Coke if B is equal to B prime, and rejects otherwise. Okay? So why is it zero knowledge? Because, well, actually we just see that the prover can distinguish between Pepsi and Coke, right? So we don't really know what the recipe is. Is it because Pepsi is sweeter or not, or some other criteria? We don't know. But then, if we think about malicious provers who don't know how to distinguish between Pepsi and Coke, what would be the strategy? Any ideas? Yeah. Yeah, exactly. So we can just sample B prime randomly, and then with probability 1/2, the cheating prover succeeds. Okay, so that was like a quick warm-up after lunch, I guess. Okay, so in this presentation, we will focus on proving lattice-related statements. And then actually, these techniques can be used to prove arbitrary NP relations. Okay, so let's move on to the next part. So now it's getting a little bit more technical. So in lattice-based cryptography, at the end of the day, it all boils down to this type of equation. So linear relation and the norm bound check. Okay, so suppose we want to prove that we know some S such that AS is equal to U, mod Q in this particular setting, okay? So it's a very standard equation. We've seen it all today and yesterday. And then, S has some small coefficients. So let's say it has coefficients -1, 0, 1. Okay, so we want to prove knowledge of such an S, which satisfies AS is equal to U, and S has ternary coefficients. Okay, so let's just prove it. So for people familiar with the discrete log setting, it may get, a bit similar, right? Because in the discrete log setting, we have the secret key X, and then G to the X is a public key, right? And then given the public key, it's hard to find the secret key. Okay, and with lattices, it's kind of similar. So we have the vector S. A times S is a public key, and given the public key, it's hard to find the secret key. Something similar to cis or inhomogeneous cis. Okay, and also in terms of homomorphism, it's also similar. G to the X times G to the Y is equal to G to the X plus Y, and G to the X to the C is equal to G to the CX. On the other hand, for lattices, we have AS plus AY is equal to AS plus Y. And C times AS, where C is a scalar, is equal to A times CS. Okay, so it seems that for people familiar with the Schnorr identification protocol, we may have hoped to switch it in the lattice setting. Okay, so let's just recall what it is. So in the Schnorr ID protocol, we want to prove knowledge of an exponent x such that G to the X is capital X. And how do we do that? The prover starts by sampling a masking Y. Is this laser working? Oh, cool. It starts by sampling the Y and computing the capital Y, which is G to the Y. And then it sends the Y. The verifier picks a challenge random element over ZQ to be C and sends the C. And then the prover outputs Z equal to Y plus CX. Okay, so that's the Z. So now, the verifier just checks that G to the Z is equal to the capital Y plus capital X to the C. And why does complete this hold? Because remember that, let's consider G to the Z. We know Z is equal to Y plus CX. So G to the Z is G to the Y times G to the CX. G to the Y is the capital Y, and G to the CX is capital X to the C. Okay, so the completeness holds trivially. Okay, so what happened? Okay, so now let's make it more interactive. So you saw the Schnorr protocol. So now I'll give you 2 minutes to say hi to your neighbor and discuss how to translate the Schnorr protocol in the lattice setting.
One quick question: what is the norm? Is this the infinity norm, or is this some other norm?
Sorry, who is speaking right now?
I am speaking.
Oh, so throughout the talk, I will talk about infinity norm only.
Okay, infinity norm only. Okay, thanks.
Okay, so let's just continue. I hope you had a very nice discussion and you met nice people. Okay, so let's just continue. So probably most of you got it. So what we will do is that now our mask, so I'm really translating to the lattice setting, so it will be wrong. But I will start with a mask y, which is a vector, and I compute w equal to ay, so I send the w. Then the verifier picks a random challenge c, and the prover outputs z equal to y plus cs. Okay? And then the verifier checks that az is equal to w plus cu. Okay, so this protocol satisfies completeness, that's great. But now the question is, what about malicious provers, right? So in this particular setting, we can come up with a malicious prover which doesn't even know S and can still convince the verifier. So how? Well, it was kind of hinted before in the question, we don't have the norm bound. And if we don't have the norm bound, the prover can just use the linear algebra to come up with any z such that az is equal to w plus cu. Okay? So then we have to put some norm bounds, right? So we need, let's say we need that the the norm of z is at most gamma. So when I say the norm, I will talk about infinity norm. Okay, so the largest coefficient in the absolute value. Okay, so if we put this norm, then what happens for an honest prover? So if we need z to be short, so z is equal to y plus cs, right? So then y also has to be short. So then y has to be short, and also c has to be short, because otherwise the norm of z blows up. Okay, so we have to make sure that all these things are also short. Okay, so we need to pick somehow the distribution for y and the challenge space for c. So my attempt would be that, okay, so let's have parameters alpha and delta, and y is picked from this interval minus alpha and alpha, and c is from the interval minus delta and delta. Okay, so then if alpha and delta are kind of short, then z will be short. And actually, we can compute some naive bound for z, which will be alpha plus beta delta by the triangle inequality. Okay? But then, well, malicious prover again. So if c is between minus delta and delta, so suppose delta is 1. So c is either minus 1 or 0 or 1. Then we can think of this the same malicious prover as for the Pepsi and Coke experiment. So it could somehow guess what the challenge would be. Okay? So the malicious prover could start by guessing some c prime and hoping that c prime will be c. Okay? It will also pick any short z and compute w equal to a times z minus c prime u, which corresponds exactly to the verification equation. Okay? And if c is equal to c prime, it sends the z. And you can see that if c is indeed equal to c prime, then the malicious prover actually convinces the verifier. Okay? So that in particular, the probability that this happens is 1 over 2d plus 1, 2 delta plus 1. So what are the issues with soundness? Well, if we want to have negligible soundness, so we want small cheating probability, then delta has to be big. But as I said, delta has to be much smaller than q. So if, let's say, delta is exponential, then q is also exponential. So then our scheme doesn't become very efficient. Okay, so what's the strategy here? So kind of informally, we want to work over rings where the ring element C could be short, whatever that means, but the challenge space is big. Okay, so for this particular case, we will use the same polynomial rings as introduced yesterday. Okay, So for this particular reason, we will work over RQ. So what is RQ?
So
yeah.
I have, if we wanted to circumvent it, if you can go back a slide earlier. Like,
yeah.
So like suppose that beta is small. Then we could just do a check over all the coordinates, and for each coordinates of S, prove that Si is in like -1, 0, or 1. Mm-hmm. And that obviously that's not constant in beta, but that avoids those issues that you're mentioning right now.
Sorry, so what's the strategy?
So the idea would be to do the conjunction of proofs and then prove this norm separately, and prove this norm by saying a conjunction of statements about each coordinate. And for each coordinate, it's a simple statement that Si is one of the values in list of length beta. So for instance, if beta is equal 1, then you would just say that beta, Si is -1, 0, or 1. Yeah. Then this grows, obviously,
with
if you
beta.
increase the beta.
Yeah.
But otherwise, this avoids the issue with the exponential hardness of LWE that you're mentioning. Does this have any issue that I have missed?
When you say that you want to prove that, let's say, each Si is -1, 0, 1, then you say that use some generic proof system for that. Is this what you're saying? Is this what you're suggesting?
Yeah, kind of implicitly. That's something that I'm sweeping under the rug, actually.
Yeah, because like then there is the main question is, okay, what's the point of this if we can just use some generic snark for this?
Yes, like a chicken and egg problem.
Yeah.
You reduce the problem to the problem one can solve.
Yeah, thanks.
Yeah, later on in the second talk there will be more comparison with more generic approaches. Okay, so it's been a long day. So we will work over this ring RQ, where F is x to the d plus 1, where d is a power of 2. It's a ring of integers of the power of 2 cyclotomic. And let's just do a very quick exercise of that. We're familiar with this ring more. So let's just compute x cubed plus 4x times 3x squared minus 1 over RQ, where Q is equal to 7. Okay? So now, what's going on if we want to this type of operations? We just multiply it, right? Like just some polynomial multiplication. And then at the end, we need to reduce mod x to the 4 plus 1, and also modulo 7. Okay, so if if you're fast with calculations, then you can verify that if you multiply these two, then we have 3x to the 5 minus x cubed plus 12x cubed minus 4x. And for the x to the 5, we know we want to reduce it mod x to the 4 plus 1. So x to the 4 is minus 1. So that's why 3x to the 5 is minus 3x. So we end up with minus 3x minus 11x cubed minus 4x. And then taking mod 7, I get 3x cubed. Okay, so just to recall, we multiply like polynomials, and then we do mod x to the 4 plus 1, and then we do mod q. Okay, so we are interested in the case when we're working over this ring, right? So we need to make sure that short times short is short. Okay, so as I mentioned before, we work with infinity norm. So for a ring element A, I take the norm of A to be the maximum of all the absolute values of AI. Okay, so now we have this lemma that A times B over that ring is at most D times norm of A times norm of B. In particular, this lemma says that if A and B are short, then A times B must be short. Okay? So how to prove it? Well, let's just write down everything. So I have this A as the sum of AI x to di. I have B, which is the sum of bj x to dj. I could just multiply all these things together to have a big sum of all the ij's, AI, bj, x to the I plus j. Okay? And now I need to reduce it mod x to the d plus 1. So if I plus j is bigger than d, or like at least d, then we can reduce it, right? But then if I look at the kth coefficient of a times b, when I say kth coefficient, I mean the coefficient next to x to the k, then one can see that the absolute value of this would be around the sum of all the ij's, such that I plus j is k mod d, and then some plus minus ai bj, right? And then for this, we will use Cauchy-Schwarz inequality to get the square root of sum of squares, and then naively just bound all these by the infinity norm. Okay, so that's a very simple proof. Any questions so far? Yeah.
Is the reason why you avoid parallel repetition is for efficiency, right?
Yeah.
Okay.
I don't want to repeat 128 times. Okay, so now let's take a step back and say, okay, let's prove such equations like AS is equal to U over RQ. So now everything is over RQ. Vector S has small coefficients, for example, minus 1, 0, 1. And also I will use this notation S beta to denote all the ring elements which have infinity norm at most beta. Okay? So I can just translate all these things in the polynomial ring setting. So what's the change? So the change is that I sample the polynomial vector y, which has infinity norm alpha. Compute w equal to ay, and then I send the w. Okay. The verifier sends the challenge c, which has infinity norm at most delta. Then the prover sends z equal to y plus cs. So then it's short. And now the verifier checks that az is equal to w plus cu. It's the same thing as before. And now for the norm, we use the lemma before, and that's how we get the d term in the norm bound. So alpha plus db delta. Okay, so the change here is that the challenge space is not just 2d plus 1, sorry, 2 delta plus 1, but it's 2 delta plus 1 to the d. So this polynomial ring structure allows us to have an exponential challenge space. So, and in particular, we can get, at least for simple attacks, we can get negligible soundness. Yeah?
So I was just wondering, suppose you wanted to stick with the
integer
lattices, not ring. Suppose you want to stick with the simple lattices with algebraic stuff. Can you take a challenge that's a small matrix and multiply from the right?
So the answer for this is the second talk, so please be there. Okay, so we managed to defend or avoid some simple cheating strategies, but how to actually prove knowledge soundness. Okay, so now it's getting a little bit more technical. So we saw already that delta, the parameter delta, corresponds to the soundness errors somehow, right? So delta and d, right? So delta will be responsible for the knowledge soundness, and then alpha will be more related to zero knowledge. Okay, so to get towards knowledge soundness, people consider the following notion of special soundness. You'll see later why it's interesting. Well, it's interesting because it's easy to describe, and it's much easier to describe than knowledge soundness. And then it was shown that special soundness implies knowledge soundness. Okay, so what is special soundness? So the special soundness is the following. So now we're back to the Schnorr identification protocol. So given two valid transcripts, okay, so the transcript for which the verifier accepts, with the same first message, and two different challenges, C and C prime. Okay? One can extract the valid witness. So that's the property of special soundness. Okay? And in particular for the Schnorr protocol, we can do that. So we have these two verification equations, g to the z equal to y times x to the c, and g to the z prime equal to y times x to the c prime. So by dividing all these, we can get g to the z minus z prime divided by c minus c prime is equal to capital X. So in particular, we managed to extract the exponent x star. Okay? And what's important here is that if c is not equal to c prime, and if we work over the field, then c minus c prime is invertible. So we can actually define x star. Okay? So now a little bit more motivation why we care about special soundness, or like why is it nice? So why is special soundness cool, unlike this room? Well, so suppose we have a cheating prover. Okay, so cheating prover can convince the verifier with some high probability. Let's say it's more than 1 over the challenge space, right? Because if it's 1 over the challenge space, we can actually build one. So that's the guessing one. And also for the purposes of this talk, to make it very easy, assume that it's deterministic. So what does it mean deterministic? It means that the first message is always the same. Okay? So what I want to do is that if it can convince the verifier with high probability, then I can use this box and run it a couple of times and extract the witness myself. And this shows that, intuitively, this box must have known the witness. Okay? So how is this strategy? Well, we consider this table, which is indexed by all the possible challenges. So C1, C2, C3, up to C, the size of the challenge space. Okay, and I can write this table. I mean, it will be a very long one. And then for each entry, I can put a 0 or 1. So I can put 1 if the adversary succeeds for that challenge CI, and 0 otherwise. So if the success probability of epsilon of the adversary is epsilon, then the fraction of 1s in this table is exactly epsilon, right? Because the probability is when I pick C uniformly at random. Okay? So if I have special soundness, then I just need to extract from 2 1 entries. So then I get some CI and a different CJ. And then from that, I can extract just by the special soundness property. Okay? So what's this extraction strategy? What I will do is I mean, very intuitive. I will sample a CI. So I will sample a random entry in this table. Okay? I check if it's a 0 or 1. If it's 0, I abort. Okay? If it's 1, then I end up in a loop where I will pick another entry uniformly at random until I get another 1 entry. So until I get another, let's say, CJ, for which the adversary succeeds. Okay? Because then, if I get that, then I will actually end up with 2 transcripts with the same first message, where CI and CJ are different. And then by special soundness, I can extract. Okay? So now the question is, what's the runtime of this strategy? What's the success probability, and so on? So in terms of the runtime, especially the expected runtime, if I define the event that this strategy succeeds in the first, in the if, so in this step, if the adversary fails. So when I say success, I mean we pass this step. Okay, so the actual probability that we succeed in that second step is literally epsilon, right? Because CI was picked uniformly at random. So the probability of not success is 1 minus epsilon. Okay, so now what I need to do is that explain the big term here. So what is the big term here? So suppose I end up in this loop, okay? So how many ones do I have in this table? I have epsilon times the size of the challenge space, right? And if Ci, if I'm in this loop, this means that Ci was one entry. So if I remove Ci, I have epsilon times C minus one entries left. Okay? So the probability that I hit another Cj, which is a different one entry, is exactly epsilon times the size of C minus 1 divided by all the possibilities. So the size of C minus 1. So in expectation, I end up with this many, with this particular runtime. Okay? And there's also 1 because I need to run this guy once at the beginning. So now if I just expand all these, then I get that the expected running time of, the expected number of running this box is at most 2. So this is like a very simple case for the deterministic scenario. Okay, and for the success probability, it's also very nice, because if the epsilon is bigger than 1 over C, then there must be at least 2 one entries in this table. Oh. Interesting. So there must be at least 2 one entries in this table. So if I hit 1, then at some point I will hit another one. So the probability of succeeding in this extraction strategy is exactly epsilon. So this is like a very, very simple case. It's more involved in the case when we have randomized cheating prover and we deal with like a 2D table and we use like heavy row lemmas and so on. But that's kind of the gist of it. So any questions so far? Yeah.
Yeah, I can try. So I just wanted to ask about being exponential. So in general, in like some number theoretic cryptographic constructions, we can have like a very big Q work over a very big finite field, but in these lattice-based things, it becomes too inefficient, I guess.
Yes, yes. Like
because of course in binary we still have the logarithm, right, for the length of the number, and then we can still do the operations like in polynomial time, but
still, yeah. So the main reasons is efficiency. Like with the most efficient schemes, for example, with Kyber discussed yesterday, what was the modulus, like 3,000 something, right?
Yeah.
So we really want to have small modulus.
Yeah, yeah. Okay. Thank you.
Any other questions? Okay. If not, then let's just move on. Hopefully the screen doesn't disappear this time. Cool. So, special soundness in the lattice setting. So can we get the same thing? Yeah, I guess because the talk is more than 2 hours or something, then you can guess the answer is no. So we have 2 valid transcripts, WC and Z, and WC prime Z prime, where the first message is W, but the challenges are different. C and C prime are different, okay? So now the question is if I can extract the original witness S prime, S star. Well, what we can do is that we can write down these equations, these verification equations as before. So then, as before, I extracted something which seems similar to the witness. So A times Z minus Z prime divided by C minus C prime is equal to U. But what are the problems here? Yep.
Well, we get the norm.
Sorry?
The norm again, or?
Yes, yes. So the answer was the norm, but I would say that even, yes, right. Even that, the question is whether C minus C prime is invertible. Can we even define that, right? So the first thing is that division, for that C minus C prime may not be invertible, so this thing may not even exist. But then this is like an easy problem to solve, but then the second problem is that this witness that we extracted is not short. It is short divided by short, but it's not short. Okay? So exactly, what do we have? We have A times Z minus Z prime is equal to C minus C prime Z. Okay? So for this, we can define, we can try to do some hand waving and think about, okay, so maybe let's define a relaxed relation. I'm not sure if it's too low. Is it too low for the people at the back? So okay, so I can just move on to the next slide. We can define the relaxed relation. So we have S star and C star such that AS star is equal to C star U, and S star and C star are short. Okay, so in particular, yeah, if C star was 1, then kind of we're there. But we don't even know if C star is 1, okay? So actually, this relaxation is fine for signatures. But it's a bit annoying, right? So,
the problem is stronger with the guy. It's not enough a level of the Can you maybe use the mic? Like you need this and delta, right? It's not this 2 alpha plus beta delta. That's this relation.
Yeah, maybe I can. Okay, the microphone is already there. So.
Okay, so here the prover needs to have the witness in S beta, right? And we are only proving that we are in S with Warsaw parameters, so
yes.
we're losing something, right?
Yes, exactly. So that's why it's relaxed, kind of. So we start with, let's say, a ternary witness, but at the end we only prove something much weaker than what we wanted. Okay? And actually this relaxation is fine for signatures, but we didn't manage to do what we wanted to do. And just a sneak peek, the second part of the talk, so after the break we'll focus on how to prove things exactly. Okay, well, we really want to say that what we extracted, so the S equal to S star divided by C star, is indeed, it belongs to S beta, or like it has small norm. So this is our candidate witness, right? So is it well defined? Well, if we pick parameters in a nice way, then we can prove that a short non-zero element has an inverse. Okay, but then so the S is defined, but S is not short. But maybe there's still something meaningful here. So one meaningful thing I want to describe, which will be used primarily in the second part of the talk, is a somewhat binding thing. Okay, so suppose I run extraction twice. Okay, so I have S0 star, C0 star, and I have S1 star and C1 star. And for each of them, I can define my, wishful thinking, my candidate witness. So this lemma says that actually, if I construct this candidate witness, then they are the same under the modules' assumption. Okay, so that's the lemma. And the proof sketch is the following. So I just write 0 equal to one term minus the same term, which in the first case is C0 star C1 star U minus C1 star C0 star U. Okay, and then we use the fact that C1 star U is equal to A star 1. And for the second part, we use that C0 star U is equal to AS star 0, AS 0 star. Okay, so we end up with some short solution to A. Okay, so either this thing inside the brackets is 0, so we get what we wanted, or we found a non-zero short solution for A. Okay?
What exactly is the solution?
So the question was, why was this solution short, right? Oh, sorry.
Because it's a product of the short thing.
Yeah. I think also the microphone wasn't working, but yeah, never mind. Okay, so that's enough for knowledge soundness for now. Let's move on to zero knowledge. So we have this scheme, right? So that's where we are so far. So for zero knowledge, no information about S should be leaked, because that's our witness, our secret. So is it the case here? So to demonstrate this, let's consider the following example. So suppose delta is 1, so I have two integers, S and Y. So S belongs to -101, and Y is between -100 and 100. And suppose my S is hidden. Okay? Now I reveal Z equal to Y plus S. So yeah, so in the protocol that was Y plus CS over the rings, but here just integers Y plus S. Okay, I revealed the Z. So if Z is equal to 101, what can we deduce about S? Sorry? Sorry, what is small? Oh, it's 1. Yes, yes. So the answer was that if Z is 101, then S is equal to 1. So yeah, so in this particular case, we actually, for some case, we do reveal some information about S. Okay, and if Z is equal to 100, then we can deduce that S could be either 0 or 1. But then if Z is equal to 99, who knows? Okay? So this boils down to the idea of rejection sampling for the uniform distribution. So just to visualize what the concept was before, I pick Y uniformly at random between from minus alpha to alpha. So that's the distribution, okay? And then I have my secret S. Okay, so this S, so if I consider Y plus S, it will shift the distribution a little bit. And you can see that if there is no overlap, then I actually can, okay, so if there's no overlap, then we can definitely deduce. But even if there is some overlap, then we get a little bit of information about S. So the 99 case that we had before corresponds to this interval between minus alpha plus beta and alpha minus beta. Okay, so this is the region where no information is leaked if we end up in this interval. So how do we implement this? Sorry, there is a question. Yes.
Shouldn't the yellow line be like wider on both ends than the Y plus S line?
Right. Right. So S is fixed. So yeah. So the Y is a distribution, and S is already some number. So in particular, -1 or something, -10. Yeah. It was a bit misleading. Okay. So how we implement this? We will just have another check. We will have a check at the end. So if Z is outside this nice bound, this nice range, then we reject. Okay? So in particular, now we implement this with the if. So if the norm of Z is bigger than alpha minus the norm of CS, which is d beta delta, then if the norm of Z is bigger than alpha minus d beta delta, then we reject. Or like we start the protocol again. Okay? And then we update the bounds. So the verifier checks when the norm of Z is at most alpha minus d beta delta. It's getting hot, right? Okay. So what's the probability of not rejecting? Well, the scheme is not very interesting if we need to repeat a million times, right? So that's where setting alpha will be important. So we know that if the size of Y is small enough, then Y plus CS will satisfy this norm check. Okay, so if Y is alpha minus 2d beta delta, then if I add the CS, then y plus CS will have the norm which is within that range. Okay, so what's the probability of hitting that? So it is the probability that for each coefficient, I end up in that interval. So, so y has m times d coefficients, so that's why m times d is in the exponent. And what I have inside is the number of all the possibilities in the interval alpha minus 2d beta delta with a minus. So that's why it's 2 times that minus 1 divided by all the possible cases within minus alpha and alpha. So that's 2 alpha minus 1. Okay, then using some simple modifications, I end up with this term. Next, for this exponent, I will multiply and divide by the same thing. So I just introduced this term so that I can apply the formula for e to the minus x. Okay, so in the end, I have e to the minus blah 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 divided by alpha. Okay, and now to make sure that this term is somewhat small, I can pick alpha exactly to be the term above, which is like 2d squared beta delta m. Okay, so if I get alpha big enough, so in particular, if I get alpha big enough, then this probability of not rejecting is not bad, like 1/3, 1 over e. So in the expectation, we just need to repeat like 3 times. Okay, so we're interested in zero knowledge, right? So no information about S should be leaked, and this is modeled formally via simulation, meaning that there is a simulator who can simulate the valid transcripts of the proof, and there's no efficient adversary which can distinguish between the real proofs and the simulated proofs. Because if they cannot distinguish, then for the simulator who doesn't even know the secret, then this means that there is no information about S leaked. Okay, so how would we simulate this protocol? So we start with a very simple lemma, just for concreteness. So the distribution of Z is if we simulate a non-aborting transcript, so we don't reject, then the distribution of Z is uniform. So what does it mean? Then what I mean is that if Z, if the if statement here holds, like if the norm of Z is small, for example, if I pick any X within that range, then the probability of Z hitting that X in that range is equal to the probability that Y is equal to X minus CS, because Z is equal to Y plus CS. And because the norm of X, because we picked Y uniformly at random, then I get uniformly random distribution. Okay? And now I can simulate a valid non-aborting transcript as follows. I can start by picking any uniformly random Z. Okay? Then I pick a C as a challenge, like the verifier, and I compute W as in the verification equation. So I pick W equal to AZ minus C times U. Okay, and I output the proof WCZ. Okay, so that's how we simulate. Okay, so then for zero knowledge, I need alpha big enough so that the rejection probability is, the non-rejection is big enough, okay? So we have delta, we want delta to be, small enough, but still big enough so that this, the size of the challenge space is exponential, but then we also need to pick big enough alpha to make sure it doesn't leak any information about the secret, okay? So yeah, I think it's a good place to stop. Any questions? Yeah.
Just to be sure, so the knowledge sound is still the speaker that we obtained so far.
Sorry, could you repeat?
So the knowledge soundness that we have obtained so far is still this weaker, this relaxed relation that we get, right, so far? Okay.
Yes.
That your knowledge is already working.
Yes, we are still getting this relaxed relation so far.
Okay.
Any other questions? Okay, so let's move on to how to make the proof non-interactive. So for this, we will use a thing called Piazza-B transformation. Okay, so the idea is that we somehow want to simulate, okay, so we want to make sure it's non-interactive. So in the interactive version, we had a verifier who picks a challenge C at random. So these protocols are called public coin, just for completeness. And the idea how to make it non-interactive is to simulate the behavior of the verifier. So because C is picked uniformly at random by the verifier, we will use it using a hash function. Okay? So we will use a hash function for this. So what the transformation does is that the prover starts just like in the interactive case. So it samples Y, it computes W equal to A times Y. And then instead of sending the W and getting the C, it computes C as an output of a hash function. So then we put all the public parameters, the statement, and the W, which was the first message. And then after obtaining the C, the prover just can continue as before. So it computes Z equal to Y plus CS, the norm check, so the rejection sampling, and then it outputs pi equal to WZ. Okay, so why not C inside the proof? Because the verifier can compute C themselves. So it can compute C equal to the hash of all these things, and then just checks the verification equations as before. Okay? So now, that's like a traditional way, when we have, so if the matrix A was n times m, then the proof size would be like n ring elements for the W and Z and m elements for the Z. So n plus m, okay? Not to mention the fact that it's n large elements and m short elements. We have a question here.
Sorry, I wanted to ask this previously, but I forgot. So just about the notation, so this S delta, can I think of this as polynomials where all the coefficients, their absolute values, like, well, they're kind of bounded by this delta? And
yes, exactly. Okay. So, right. So S delta is a set of polynomials in R or RQ with infinity norm at most delta.
Okay, thank you.
So coefficients are between minus delta and delta. Okay, so the nice trick in the lattice setting is that instead of sending W, which is somewhat costly, we can just send the pi, which is C. We can just send C in the proof. So the proof is C and Z. And then to verify now, we use the fact that W can be deterministically computed from Z and C. So what was W? W was AZ minus CU. So that's the check that we have in red. Okay, so the verifier now checks that C is equal to the hash of the public things and AZ minus CU. So this informally, indirectly checks that W is equal to AZ minus CU. Okay? And why is this change interesting? Is because with the proof size, it's only one short ring element and Z of length, which is of length m. So one m plus one ring elements. Okay, so people use this optimization more. Okay, so now to get zero knowledge in the random oracle model, it's somewhat similar as before. So now to prove zero knowledge, we will use the fact that we have this hash function from the Piazza-B transformation, and in the random oracle model we can do cool stuff like programming, for example, and forking and so on. So in this particular case, we can simulate the proof somewhat similar as before. So what we do is that we sample Z as before, so uniformly random. We pick a C, and we compute W equal to AZ minus CU. But then we need to make sure that it's consistent with the random oracle equation, so we program C in the right way. And then we output C and Z. Okay, and then we need to make sure that we can do that we don't override the random oracle, that we stay consistent, and so on. So there are all these like bad events to take care. But that's kind of the gist of it. Okay, so now we are ready to move on to signature schemes. So how to get a signature? So now we will discuss a signature scheme, and it's called the Fiat-Shamir with boards. So the key generation will be, so my secret key will be the secret S, okay? And the public key is the U, which we had before. So U is equal to A times S. Okay? And then to sign, we will just follow the proof algorithm. Okay, so for the signing, we sample the Y as before. We compute W equal to A times Y. We compute the hash, so the C. So now the nice modification here is that the hash function also includes the message M. Okay, so it's a hash of all the public stuff, the W, which is the first message, and the message for the signature scheme. Okay? We compute Z equal to Y plus CS. We do rejection sampling, and we output the proof. Okay, and to verify, it's literally the same as before. So to verify, we check that Z is short, and C is equal to the hash of the public AU and AZ minus C times U and the message M. Okay, yes.
Capital A is also part of the public key, right?
Yeah.
Yeah, because
right.
we just have U. Okay, and the other question is for the zero knowledge in the random oracle model. So if we then instantiate it, we don't really need a random oracle model for the zero knowledge part, right? Or
sorry, what do you mean by we instantiate?
Like, no, I mean, so in practice we would use some hash function.
Yeah.
And I'm just curious if this proof of zero knowledge really requires the random oracle model, or if we can also get zero knowledge without the random oracle model. Because in any other constructions you don't need the random oracle model, like for classical snarks in the D-log-based snarks, or like, yeah.
So for zero knowledge in the non-interactive setting, we kind of do need a random oracle model. It's because of kind of the ordering. So we can compute W if we know C and Z. Okay, if we don't, so the advantage of random oracle is that I can compute that C. I mean, I can sample the C, and I can compute the W, and then I program C to be what we want. If we have a standard hash function, we wouldn't be able to kind of rearrange the steps. See what I mean?
Yeah. Okay. I think I know. I confused it with some proof systems where the order doesn't matter, and maybe that's the difference. Yeah. Okay.
Oh yeah, like the schemes use random oracles in different ways. Yeah.
Thank you.
Okay. Okay, so the only modification is that we put the M inside the hash function. So now, very briefly about the security of the signature scheme. In my previous version of the slides, I put like the proof sketch with a forking lemma and so on, but I decided that probably in the afternoon that would be too much. So this is a very brief overview of unforgeability. So we talk about unforgeability of the signature schemes. So what is unforgeability or strong unforgeability in the random oracle model? So we have an adversary who has access to the random oracle. He also has access to the signing oracle, so it can query a message M and get the signature back. Okay. And then at the end of the process, it outputs a pair M star sigma star. And the winning condition here is that the adversary wins if it's a valid signature sigma star for a message M star, and that pair M star sigma star doesn't belong to the query answer set that the adversary queried. Okay. So the adversary can't have seen this this pair before. Okay, so which is very natural. Okay, so okay, so there are like some notation, but we won't use it anymore because I removed the forking stuff. So the unforgeability proof usually goes like this. So the first step is we use the signing oracle, right? So the idea is to replace the signing oracle, which uses the secret key, with an oracle which just simulates the proof. So here we use the zero knowledge property. Okay, and for this simulator, we won't be using the secret key anymore, so that's nice. So the second step is to do some rewinding for the adversary. So that's where we would use the forking lemma. And then after the forking lemma, we use our special soundness property, meaning that at the end of the day, we will be able to extract two different proofs with the same first message and two different challenges. And for that, we can apply our extraction as before. But as already mentioned, we still end up with the relaxed case, right? So at the end of the day, we still end up with equation like this. So A times Z minus Z prime is equal to C minus C prime U. But now what's interesting is that we know what U is. U is A times C minus C prime S. Okay? So we need to argue, what we want to argue is that we found a short solution for A. We can prove it's short. All these things are short, right? But we want to prove that it's non-zero. And for this, we can use possibly some more fancy stuff. But here we'll consider this simple lemma. So the lemma is as following. So the lemma says that if I have the matrix A, then if I pick a secret key S, then there exists another corresponding secret key S prime such that AS is equal to AS prime. Okay, so in more detail, if I have a matrix A, which is long enough, so M is at least 2n times log Q divided by log 2 beta plus 1. And if I sample S, then with an overwhelming probability, there will be another valid secret key, which maps to the same public key. Okay, and how does this proof go? So the proof says that this technique was already used a few times throughout the summer school, but we can think of A as a linear transformation whose range is Q to the ND, right? So there are at most Q to the ND elements in S beta to the M, which are kind of lonely. So I call them lonely because they don't have any other pre-image. There's no any other pre-image which maps to the same image. Okay, so there are at most Q to the ND lonely elements, right? Because if there were more, then by the pigeonhole principle, we could map them to the same image. So at the end of the day, the probability of an element S of the vector of the secret key S, which is lonely, is bounded by this fraction. So Q to the ND divided by 2 beta plus 1 to the MD. And if we pick parameters nicely, then it's at most 2 to the minus D. Okay? So we use this lemma to deduce that, okay, so like the adversary doesn't see doesn't know any information about S apart from the public key. So it could have been S or S prime. So with probability 1/2, we can end up with a case where this thing is non-zero. Okay, so that's how we obtain, that's how we reduce the unforgeability to the security of module sys. Any question about the sketch or anything so far? Okay, so now we kind of covered things, you know, the signature scheme, which is similar to the lithium. So what's the difference? So there are a few differences. So the first one is that the scheme applies various optimizations, for example, low-order bit compression, compressing the public key, and so on. We don't want, the scheme tries not to do forking, because this ends up with a reduction loss, which is linear in the number of random oracle queries. So for this, they focus on a kind of a slightly tailored assumption, which is like a self-target module sys. And also in this talk, I really gave very naive bounds everywhere, and this can get improved for sure. So what I didn't mention is there are a few things. So the first one is rejection sampling, where we don't focus on uniform distribution, but we do discrete Gaussians. Okay, so this is like another technique where we can use discrete Gaussians everywhere, and that's really helpful if we prove statements. Let me just go back. Can I go back somewhere near? Probably not. Okay, so the discrete Gaussian rejection sampling is especially useful if we want to prove knowledge of a short S, but the shortness is in Euclidean norm rather than infinity norm. So that's much more efficient. Okay? Where were we? Okay, but there were also more recent works which even tried to remove rejection sampling. And we have the Raccoon signature scheme, which relies on a assumption called hint LWE, and also G plus G from AGCrypt last year. And Raccoon is one of the candidates for the additional call for signatures. And also rejection sampling for Fiat-Chemie with boards has certain technical issues. So it's not super clear that it really satisfies honest verifier zero knowledge. But for this, I'll refer to the works from Crypto last year. Okay, so that concludes the first part of the talk. So maybe, please let me know if there are questions, but otherwise I'll just start with the second part.
Right, so we still have 15 minutes, and what Khan says is that he can start now the second part, which I think makes sense.
Yeah.
So, right, unless there are some questions, we'll just let him continue.